Hello everyone, my name is William Mills and I am the head athletic trainer at Melbourne Prep School and a doctorate student at Rocky Mountain University. I am presenting today on exercise-associated muscle cramps and what is optimal hydration strategy to prevent them. First, I would like for us to look at this concept map and I want to give you an overview of where we are going. First, we will start with some review of muscle contraction, which leads us to the cramping and the factors that contribute to this cramping. And then we will move to preventive strategies. Exercise-associated muscle cramps is also known as heat cramps, even though the only association is that the majority of these cramps occur in hot, humid weather. But not all the time, and these kinds of cramps can sideline players. This form of cramping involves involuntary painful spasms of large muscle groups and spurs ongoing debate on etiology, prevention, and treatment, says Valentine 2007. Stoffen et al. 2005 stated, "What is puzzling is why some players are predisposed to heat cramps, yet others on the same team with similar physical characteristics in the same environment are seamlessly not." Let's start with a review of some of the basics of human physiology and how a muscle contracts. Hopefully this will give us a clue to why a muscle does cramp and what we can do to prevent it. For most of you, this should be a review. We must first start in the peripheral nervous system with the motor neuron. All cells, including our motor neuron, and if you kind of look up in this area here, in the upper left-hand corner, have a resting potential with the interior of the cell negatively charged with respect to the exterior. Sodium and chloride are necessary for a cell to have a resting potential, which means essentially a reduction of charge across the plasma membrane of the axon. The cell, or in our case, the motor neuron, you get right in this area, and it leads in this direction here, is the nerve that innervates the muscle cell or fiber. And this here is our muscle fiber and cell, which means the same thing. So the cell opens the sodium pumps to reduce the resting potential in the neuron, and the cell gets excited. During this excitement of the cell reaches a certain voltage, and it will open even more sodium channels, producing a wave of depolarization along the axon. Along with the sodium coming into the cell, potassium is exiting the cell as part of the depolarization. This is called the action potential, and for a neuron called a nerve impulse. Let's not forget and keep this in the back of our minds that all this does not occur passively, but it can only occur if there is energy from the breakdown of adenosine triphosphate, or ATP. So now we have this electrical impulse driving to the muscle fiber. Now what? I'm going to do an overview of the process for muscle contraction. In order for a muscle fiber to contract, it must get an electrical impulse, or action potential, from the nervous system as described earlier. The action potential reaches the end of the motor neuron to structures called synaptic vesicles, and they contain a neurotransmitter, which is a chemical called acetylcholine, which stimulates a muscle fiber. When the action potential gets down to the end of the neuron, it will cause these synaptic vesicles to release acetylcholine. The acetylcholine will then cross the synapse, the physical gap between the motor neuron and the muscle fiber, located right here on the motor neuron. So it's really small right there, and binds to acetylcholine receptors. So the signal goes down the motor neuron as electrical, but the signal across the synapse is chemical. Isn't that cool? If enough of these acetylcholine neurotransmitters bind to receptors and sodium channels open in response to this depolarization of the neurotransmitters, it will then permit a huge flow of sodium ions to enter the muscle fiber, inducing an action potential in the muscle fiber. And that will induce the muscle fiber to release calcium from the sarcoplasmic reticulum. Now before I go over muscle contraction, let's go back to the synapse. Once the acetylcholine binds, it can't just stay there, because if it did, it would keep the muscle in a constant state of contraction. So within the synapse, there's an enzyme called acetylcholinesterase. What this acetylcholinesterase will do is break down the acetylcholine molecule, and stimulation will stop. In reality, all this happens within milliseconds. Now let's talk about what happens when calcium is released in the muscle fiber itself. The calcium from the sarcoplasmic reticulum goes and binds to the active site on actin. When it binds the active site on actin, opens this active site, which allows the myosin cross-bridge to bind to that active site. You should remember, when we need to break down the molecule ATP again, that we need to break down the molecule of ATP again in order to produce energy for this action to occur. This energy allows the myosin cross-bridge to ratchet up. Then it is going to use another ATP to produce energy in the myosin to allow it to let go. As long as the acetylcholine is stimulating the muscle fiber, that active site will stay open. The myosin cross-bridge will let go, grab another one, latch it, let go, and so on. Pulling the Z lines of the sarcomere closer to each other, and that is muscle contraction. Now once that signal stops from the acetylcholine, no more binding of these receptors will occur, and this will cause the calcium to be actively transported back into the sarcoplasmic reticulum. Without calcium, the active site is closed on the myosin and no longer bind, and the sarcomere goes back to its resting length. In addition, sodium channels close, potassium channels open and exit the muscle fiber. Chloride channels also stay open. These ions of sodium, potassium, and chloride all contribute to the depolarization and repolarization of the muscle fiber. So after that quick review, one can guess that at any point there's a disturbance in any of these processes, then the muscle will not function properly. So here we are. Let's say there is a football player in the third quarter of a football game on a moderately hot September day, and this football player starts to cramp up. What are the factors that contribute to this cramping? So here we are. We're going to start in our concept map right here at the muscle cramp, and we're going to start looking at some of these factors that contribute to and cause muscle cramps. There are several factors that can cause muscle cramps, and if we investigate these factors, then we can produce a prevention strategy for our football player. One of the first potential causes is depletion of fluid or dehydration. So we're moving from these factors, and we're following this line here, the arrow, to this part of our pyramid. Now I put fluid on the top of this pyramid because it does contribute to muscle cramps. And if it does contribute to these muscle cramps, it will do so in a small and secondary way. We know it from the American College of Sports Medicine that if we lose greater than 2% of our body weight, again, following our concept map, if we lose greater than 2% of our body weight during practice or game, it could affect the performance of our athlete. Morgan and Sheriff's 2010 found dehydration will impair both physical and mental performance and pose a health risk. Fluid replacement strategies are essential in exercise situations where large sweat losses occur. So is dehydration a factor for muscle cramps? Schwalbus et al. 1997 stated, what was interesting is that dehydration was first linked to exercise-associated muscle cramps in mine workers' environment in the early part of the 20th century. And the management included hydration and electrolytes. And we are still trying to figure that all out. In the position statement of the American College of Sports Medicine, dehydration alone is not reported as a primary cause of muscle cramps. Dehydration can cause muscle fatigue, stated Stoffen et al. 2005, which in turn could cause cramping of the muscle by way of excessive sweating due to intense exercise in the heat. This large loss of fluid and sodium, along with consequent contraction of the extracellular fluid space can alter normal cellular and nerve function. Miller et al. 2010 in their paper described the situation. The resulting contracture of the interstitial space increases the mechanical pressure on select motor nerve endings and finally results in exercise-associated muscle contraction. Miller et al. 2010 go on to say in their research that dehydration does not, pardon the pun, hold water, for example, regarding fluid loss in crampers and non-crampers. Plasma volume losses in runners with exercise-associated muscle cramps. 5.2% were not statistically different from those runners without exercise-associated muscle cramps, which is 4.4%. Nor were losses in blood volume, 1.7% versus 1.3% respectively, or body weight. The evidence at this time is not convincing that dehydration alone causes exercise-associated muscle cramps, and more research is needed in this area. What we do know is excessive consumption of hypotonic fluids and excessive loss of total body sodium can lead to a condition called hyponatremia. This occurs, according to the American College of Sports Medicine, when plasma sodium falls well below 120 micromoles per liter. Chances increase brainstem herniation, respiratory arrest, and death. This condition will occur more often in athletes such as marathoners who are small and less lean, who run slowly, sweat less, and drink heavily water. The caution should be shown here that even football and tennis players have had exercise-associated hyponatremia who drank too much water to treat or tried to prevent heat cramps, or when a cramping player is given hypotonic fluid intravenously, found Cramps and Kahn 2010. Let's now address the factor of electrolytes, which is right here in our, again, going from our factor, we're going to bridge down to here and follow this possible depletion of electrolytes as a cause or factor of these muscle cramps. And this is on our second level of our pyramid. Here the research is strong, but still there are some misnomers surrounding what electrolyte is causing muscle cramps. If one remembers in the beginning of this presentation, we discussed the pathology of the action potential of the nerve and muscle contraction. Many ions, electrolytes, are involved, so coaches, athletes, parents, and experts in the field of sports medicine contribute muscle cramps to the loss of potassium, sodium, chloride, and even magnesium. I'm here to tell you that if you overtreat with supplementation without knowledge, then you can do more harm than good. Take, for example, supplementing with potassium. Again, what I did here is if you have this electrolyte and we travel here and we're supplementing with this with this potassium, it can be dangerous. For years, it was recommended to eat bananas in order to prevent muscle cramps. There are electrolyte tablets out there, which I have personally used with athletes, but no longer do, which have high concentrations of potassium. Echner 2007 reported a sweat sample study with crampers and non-crampers for analysis of sodium and potassium in sweat. Sweat potassium was similar between the groups, but sweat sodium was more than twice as high in crampers as in non-crampers. If you have too much potassium in your system, then you can have a condition called hyperkalemia. The body needs a delicate balance of potassium to help the heart and other muscles to work properly. Too much potassium could lead to dangerous and possibly deadly changes in the heart rhythm. Obviously, we are talking about extremes. Michaelis et al. 2007 report that if an athlete has a sickle cell episode, and that athlete was taking some form of potassium supplement because he or you thought it would help his muscle cramps, this mistake could prove deadly very quickly. Now let's look at the electrolytes and go in the other direction and come down here to what we call salt. Now let's look at this. Or the breakdown is sodium chloride. Again, early in the discussion, I reviewed how important chloride and, more importantly, sodium pumps are in the normal function of cells, but more specifically, motor neurons and muscle. So it would only be fitting to investigate these ions as culprits to muscle cramps. In a study by Bergeron, 2003, reporting a sweat study on runners, there was a significant loss of sodium difference between crampers and non-crampers. It has been hypothesized by Bergeron that excessive sodium loss in sweat results in the development of exercise-associated muscle cramps without altering serum sodium or chloride concentrations. Because sweat sodium concentration is always hypotonic, explains Schwellnus, 2009, as significant loss of sodium through sweat can therefore only occur if there is an accompanying large loss of fluid. So again, this is the connection between fluid here and sodium for muscle cramps. Dehydration would accompany any significant sodium loss in athletes presenting with exercise-associated muscle cramps. However, Schwellnus, 2009, continued that salt sweating alone does not cause cramps, but the combination of dehydration, sodium and chloride loss in the sweat, and now what we will address what we will address next is our last factor that we're addressing is muscle fatigue by way of neuromuscular control, and what is being referred to as the new triad of muscle cramps, which is the fluid, the electrolytes, and the neuromuscular fatigue. Let's keep in mind that muscle cramping in athletes may occur as a result of many underlying conditions. The pyramid I developed is a way of showing how much each area may contribute to the overall problem. So how does this neuromuscular thing work in relationship to muscle cramping? Brolick et al. 2013 proposed through their research a combination of increased excitation from 1A muscle spindles and decreased inhibition from 1B afferents, Golgi tendon organs, or GTOs, cause altered alpha motor neuron activity leading to the onset of cramps. Miller et al. 2010 stated that this tends to occur when the muscle is contracting in an already shortened position. Miller explains the reduced tension in the muscle tendon likely reduces the inhibitory feedback from the GTO afferents, thereby predisposing the muscle to cramp from the imbalance between inhibitory and excitatory drive to the alpha motor neuron. This enhanced excitability at the spinal level results in an increase in alpha motor neuron discharge to the muscle fiber, producing a localized muscle cramp. However, even this theory has limits, such as how fatigue a muscle needs to become for an exercise-associated muscle cramp to occur, or whether the neuromuscular fatigue is occurring peripherally in the muscle or centrally in the spinal cord or brain. What is interesting is that there may be different types of exercise-associated muscle cramps, and Young et al. 2005 reported that fatigue-induced exercise-associated muscle cramps by way of the neuromuscular factor tend to be more muscle-specific, whereas heat-related exercise-associated muscle cramps may be more widespread, and that would be our sweaty salt athletes like the one football player in our earlier example with factors from fluid and electrolytes. This all leads to the prevention strategies. So here we are, we had our muscle contraction, we discussed some of the factors, and then from these factors, and even the factors that apply, that we want to apply to prevention, but we also want to apply the non-use of potassium as part of our prevention strategies. So that's why I pulled all these together, and when we bring this arrow down to here, we're now visiting the prevention strategies for muscle cramps. We can guess one way on how to do it, so we can guess what to do and develop hydration strategies, or we could be very specific in our design. So by being more specific, we can identify more of the issues that, again, are very specific to that athlete, like measuring fluid difference by weight. Again, that's what we have here. So by measuring the weight, we can come up here and we can see whether or not somebody's becoming dehydrated by weighing before and after practices, and whether or not they're heading towards dehydration, a dehydration state. The other thing we would do is have an athlete wear a patch. Again, one of our specific designs, and that will measure the sweat content. And in that sweat content, we can see how much sodium the athlete is losing. And from there, we can also collectively we can develop a hydration strategy. Depending on the outcome of this hydration strategy can be developed, which we will talk about in a minute. If the athlete is not dehydrated and the electrolytes in the sweat are within normal limits, then we can start to target the neuromuscular. So we can actually go back here, this area. So we're looking at all our factors. We can jump through. We don't even have to go through there and apply what we know here. We can just know what our factors are, which can, again, will lead to our prevention strategies. And if dehydration or sodium are not an issue, as in here, then we would address the neuromuscular training, and hopefully that will take us to having that person have reduced cramps or no cramps at all. But our main question is about hydration. Now, just briefly talking about neuromuscular training, Miller et al. 2010 suggests doing exercises that target muscle spindles and GTO receptors to delay neuromuscular fatigue onset and hence exercise-associated muscle cramps. Plyometric exercises may be beneficial, enhancing efficiency and sensitivity of reflective and descending pathways used in neuromuscular control. Also, endurance training may also serve as effective means of preventing exercise-associated muscle fatigue by expanding plasma volume in the extracellular fluid compartment and delaying neuromuscular fatigue. Valentine 2007 reinforces that there is a significant variation in both sweat rate and sweat sodium concentration among individuals participating in the same event or practice. It is difficult to put together a guideline for fluid and electrolyte replacement that applies to everyone. So that's why guessing does not really work. But the question before us is, what is the optimal hydration strategy? Knowing what we know now, we can make an educated conclusion. Bergeron 2003 suggested we do not have a sweat test. Bergeron suggested if we don't have a sweat test, at the first sign of any kind of twitching, muscle twitching, one needs to consume 16 to 20 ounces of a sport drink with a half a teaspoon of salt, which is approximately 3 grams, added and consumed all at once, if able, or over a 10-minute period, with little additional water, has been shown in relieving and cramping or preventing switches from developing any further. Additional strategies Bergeron 2003 suggests is to consume 32 ounces of sports drink with a quarter teaspoon or 1.5 grams of water and consume it over a period of an hour during the game or event. So here we are, we're discussing the hydration strategies for pregame. Pregame could be the day before or right before the game. And Bergeron suggesting that those that are crampers take the 32-ounce drink with 1.5 grams of salt during the game and consume that over an hour period. As for recovery, so now we're at post-game, his suggestion is to make a recovery hydration drink with a 32-ounce sport drink with a half a teaspoon or 3 grams of salt. And the number of these post-game recovery hydration drinks depends on how much you weigh and how much you lost during a game. So for every 1 kilogram of body weight loss, an athlete should consume one of these 32-ounce recovery drinks with 3 grams of salt in it. Now we could take it one step further and do a sweat study and see what and how many ions are lost during a practice or game. So that would be kind of in the guessing range by doing this, adding the salt to the sports drink. But earlier, if we did a sweat study and we know how much weight the athlete was losing and what the content was, there are companies out there which analyze a sweat patch that can be done to develop these hydration strategies. And from that analysis of sweat, the company, from the sweat that is analyzed, the company would produce a product that is even more specific for the problem of the athlete and more specific than what Burger Ron recommends. And they will produce a product that you would take pre-game, during a game, and post-game. In summary, muscle cramps can occur from various conditions. As an athlete trainer, many times we have to be a detective and investigate by problem solving and taking all the clues to find out what causes an issue. From there, we need to research the evidence and apply the best strategies. Thank you for listening, and if you have any questions or want a copy of the reference list, then please email me at wmills@malverprep.org. Thank you.